Is it too late to ask a question, Professor?
No.
Yeah, I just got a question about the homework.
Okay.
And
And what might your question be?
I'm trying to find it. Oh, sorry, one second.
Oh.
You know what? Let me just get back to you after.
Okay. Anyway, we're going to finish up chapter 17. And so I said last time that we would review the titration part. And the thing I want to point out is really not much new. And in the chapter, we learned about moles per liter, right, as a concentration. So what works in stoichiometry is simply moles. So no matter what, whether we start with liters or we start with grams, we have to somehow get it into moles. And then titration problems essentially give you all the information to get the moles of either the acid or the base, but not the other. And you have to use stoichiometry to figure out the missing stuff. So a student titrated or neutralized 15 milliliters of a sulfuric acid solution with 35 something milliliters of a 0.2 molar sodium hydroxide solution. So in laboratory talk, we would call this a standardized solution of sodium hydroxide simply because we know its concentration. So you need the chemical reaction because you have to use the stoichiometry. And then we have to look at the problem. We don't have enough information to get the moles of the acid. We only have the volume. They're asking us to come up with the concentration, moles per volume. But we do have everything we need to calculate the moles of the base. Here's the volume, essentially liters, and here's moles per liter. So we can get moles of the sodium hydroxide. So we do that. So here's the moles of sodium hydroxide. So we went from out here in liters into moles of sodium hydroxide. Now we're going to use stoichiometry to turn moles of sodium hydroxide into moles of sulfuric acid using this relationship, 2 to 1. So we use the stoichiometry. We need to get rid of moles of sodium hydroxide, keep moles of sulfuric acid, and the 1 and the 2 come from the balanced reaction. So now we have moles of the acid. And we have enough problem to now calculate the concentration. There's that many moles of acid in 15 milliliters. So that's where we get the concentration. So here's like a picture of what we were doing. We had 15 milliliters of this. We didn't know what the concentration was. We had a burette full of this, and we knew what the concentration was. So we dripped this into here until we get to pH 7, which is neutral pH. And we see that took 35.2 milliliters to do that. So here's another one. This time we're going to be solving for liters of this. So to neutralize 750 milliliters of 0.3333 moles per liter of sodium sulfuric acid. So notice that I got the volume of the acid, the concentration of the acid. I can get the moles of the acid. So I simply did that. And then I used stoichiometry, convert that into moles of the base. And then to calculate the volume, I got that many moles of base that I need. It's in a solution that's 0.2 moles per liter. So that gives me that many liters. Okay. So here's another couple over here. This one has a slightly different stoichiometry, but it's all the same. It's the same type of thing. So the rest of the chapter doesn't have math in it. It's more or less understanding things. So we have 3 basic categories of mixtures. We have a suspension, which is heterogeneous. And so the particles in a suspension are so large that they can be removed by a simple filter or by a a centrifuge. We have a colloid where the particles are too small to settle out by gravity, essentially because there's so much kinetic energy at that particular temperature. They will pass through simple copy filters, but they're large enough to reflect light off of their surfaces, giving you the Tyndall effect. So think about milk, for example. If you pour milk through a coffee filter, isn't it still white? Isn't it still opaque? So it's a colloid. And you could theoretically make the particles of the colloid centrifuge down or with a different filter, a more precise filter. But what does it mean, the Tyndall effect? So this is a pretty good visual right here. It's not the best, but here's a true solution. The particles in this true solution are so small that they do not bounce light off of their surfaces, but in the colloid, they do. So colloidal particles are things like proteins and little droplets of fat like in milk. And you can see that the light passes right through here, and then it's hitting a particle and it's getting scattered by it. So that's the Tyndall effect right there. And then by analogy, some people will look up in the sky and say, oh my God, look, the Lord is shining his light down upon us. And then the scientists might look at that and say, oh yeah, that's the Tyndall effect of all the colloidal particles in the air scattering the light. Bums some people out. So of colloids, we have a couple of major categories. One is an emulsion. It's a colloidal system of immiscible liquids with colloid-sized droplets, such as the fat droplets in milk. This is the reason why milk is not transparent. It's opaque. A sol is a system of solid particles suspended in a liquid. Ink and paint are sols, at least before they dry. Then an aerosol is a colloidal system of solid or liquid particles suspended in a gas. So VOG and other pollutants. What we're looking at right here is also an aerosol, right? And then finally we get to a solution, which is a homogeneous mixture. It can either be a gas, liquid, or a solid. So filtered air is a solution, filtered seawater is a solution. If I take a mixture of gold and silver and I melt it and stir it all up, well, it's a solution in the liquid form, and I take the heat away, it solidifies, it's still a solution. And the thing about a solution is that the properties will change with the composition. So if I made you a drink of 1% ethanol and 99% water, you'd probably drink that all day long and not notice anything. But if I made you a drink of 99% ethanol and 1% water, I don't think you would be comfortable drinking that. So whole blood is a good example. We all have it. Sometimes it leaks out of us, but we all have it. And so I think it's a good model to describe all this stuff. So anyway, I went through this stuff about vampires. Why do you think vampires are so strong? Maybe because blood is so nutritious, right? But when I was a kid, these were what vampires looked like. They were decrepit, they were diseased, they were disgusting. And now, here's the new Hollywood type. They're hot looking. So they're hanging out with all the Hollywood movie stars, and some of them are movie stars. Yeah. Yeah, come a long way. So anyway, blood is a suspension. So here's a suspension. What happens when your blood stops moving? Well, the particles that are so heavy start to settle out. So you can either wait for gravity to cause that to happen, or you could centrifuge, which simply increases the force of gravity. And you can remove the cells, and what you would have left would be a colloid. This would be your serum. So if you take your sera and you shine light through it, you're going to see the Tyndall effect because of all the large proteins in there, things like that. And then most textbooks will just stop right there. They forget that for the last 50 years, we've had ultrafiltration and ultracentrifugation. We have an ultracentrifuge on the 7th floor. I forget how fast it goes, something like 120,000 RPM. And if I want to precipitate a protein out of there, I may have to run it for half a day. I could run it for several days. I'm going to get the proteins and everything else to precipitate out. We have ultrafiltration devices that filter out pretty much any size particle you want. Some terms of protein, for example, we have ones that separate out anything that's greater than 5,000 grams. We can go to 20,000, to 50,000, to 80,000. There's all kind of cutoff values. So we can do all that. And when you take everything out, all the colloidal particles out, you have a solution. And that includes your electrolytes. So this is an interesting story how I got this in here. So my friend, Professor Bhagavan, he passed away a couple of years ago, but he used to come down to the lab all the time and we'd have tea. So he was a biochemistry professor, originally from India, of the Brahmin class. And so we would discuss important things. And he asked me one time, did you ever hear of using any coconut water for an IV? And of course, we didn't, but I looked it up and here's actually an important publication, actually. So that was used in World War II in the South Pacific to save all kinds of American lives. So here's some definitions. Solvent is the most abundant substance in the solution. Solute is the least abundant one. Hydration is the process of dissolving in water. If it's not water, you could say the process is solvation. Then a soluble solute dissolves into the solvent while an insoluble solute will not. Miscible solute dissolves into the solvent while an immiscible solute will not. Here's where both are liquids. So oil and water are immiscible. Alcohol and water are miscible. So hydrophobic solute does not dissolve in water, while hydrophilic solute will. Phobic means to hate, philic means to love. So a nonpolar solute is hydrophobic, while polar solvent or solute is hydrophilic. So there's no strict definition between a concentrated solution and a dilute solution, but we still use those words in a relative sense. A saturated solution cannot dissolve any more solute, while an unsaturated solution can. A volatile solvent or solute or solution is a liquid that evaporates quickly. An electrolyte is a solute or solution containing dissolved ions that will conduct electrical current. And a non-electrolyte does not have ions in it and will not conduct electrical current. An electrode is simply a wire that you put into solution. So here's some examples of electrolytes. And this is probably the very first diagram I tried to draw using basically Microsoft Office. So here we have a battery, and then this wire turns into an electrode when I place it into the solution. And here's the other wire going through a light bulb. So now if I were to touch these two wires together, the light bulb would turn on. But if I keep them apart, the only way electrons can get from one end to the other and get a current going is if there are ions in the solution to basically carry the current. So what are some examples of electrolytes that would turn that light on? Tap water. There's enough ions in tap water, referred to as minerals, to weakly light up the bulb. Soluble ionic compounds like sodium chloride, obviously you're going to contain ions and turn the light bulb bright. Ionizing molecules like acids and bases produce ions when they dissolve in water. So for example, sulfuric acid produces ions in water. So does ammonia. Even though it's a molecule, same as this, they produce ions in water. And non-electrolytes will not turn the light bulb on. For example, pure water, which contains too few ions. Very insoluble compounds, not enough ions dissolve to make the light bulb turn on. And then non-ionizing molecules such as glucose. So glucose is blood sugar, it's in your blood, but it's not an electrolyte. And solubility is a type of concentration. We use it as a way to measure how much something will dissolve. We don't normally use it as a concentration, but it is a concentration. It's the maximum amount of solute that can dissolve at a given temperature in a given amount of solvent. So for example, the solubility of sodium chloride at 25 degrees is 36%. That means that you can get 36 grams of sodium chloride to dissolve in 100 grams of water at this temperature. So here I'm putting sodium chloride into water. If this were 100 grams of water, I could put 1 gram and it would be considered maybe dilute. I could put in 30 grams and we could consider it concentrated. If I put in 36 grams, we would consider it to be saturated. You can't get any more to dissolve. If I put 37 grams in here, 1 gram will go to the bottom, it will not dissolve. So what I know, if I take out any amount of this saturated solution, I know that there's 36 grams in every 100 grams of that solution. And here I'm trying to point out that the amount of sodium chloride that's dissolved may be seeming static, in other words, not changing, but it does change. The reason why it doesn't appear to change is because the rate of precipitation now becomes equal to the rate of dissolving. But that does not mean that precipitation and dissolving are not happening. They are happening. And this is a situation of equilibrium. So if you got 20 people in a room, and every minute one person walks out but another person walks in, you still got 20 people in the room. But it's not static, it's dynamic, constantly changing. So what kind of things affect the solubility? I put very first the nature of the solvent in the solute. Like dissolves like. It does not explain it, it just says what it does. And we learned about this in chapters 13 and 14. Polar molecules are like little magnets. They will dissolve in polar solvents because magnets are attracted to other magnets. Non-polar molecules are basically excluded from that. And that's the reason why oil and water don't mix. And then temperature is important. Here's what most soluble compounds do in water. If you increase the temperature, you increase the solubility. For example, table sugar. Think about trying to make hot tea sweet versus iced tea, for example. It's hard in iced tea to get enough to dissolve. So most substances are like that. Sodium chloride is unique. Sodium chloride doesn't change the solubility very much with temperature. If it did, if it behaved like most substances, then the ocean at the equator would be extremely salty, and at the poles where it's very cold would be very, very brackish. That would be pretty hard for a whale. So a whale would be struggling to stay at the surface in the Arctics, and it couldn't even dive down in the tropics because they'd be too buoyant. Did somebody have a question?
I was just wondering about the word brackish.
Oh, it's not very salty.
Oh, I see. Okay.
Yeah. And then there are a few substances that actually decrease with increasing temperature. Now, if you look at gases, gases are not very soluble to begin with. And when you increase the temperature, their solubility goes way down. And that's what we refer to as thermal pollution. So let's think about, why does oxygen dissolve in water again? Oxygen, difference electronegativity 0. It's a nonpolar molecule. The reason why it dissolves in water at all is because it's going about 1,000 miles per hour and then just bounces all around until it eventually finds its way out again. So what happens if you have hot water? So in hot water, the particles get down in here, and guess what? Their speed is related to the temperature. So they're going faster in the hot water. So they'll spend less time before they find their way out again. And increased partial pressure increases the solubility of gases. So if I got a few gas particles up here, there's going to be not so many dissolved. I got a bunch more, then I'll have much more dissolved. Okay. And finally, particle size and stirring will increase the rate of dissolving, but not the actual solubility. I remember as a kid going to sugar mills and stuff. You'd see these big, giant crystals of sucrose in different places in the vats, just like an inch across. But then eventually all get granulated. So why did they do that? If I take a cube and I just cut down the center of it, I've increased the surface area 33%. And where does dissolving happen? At the surface. Increase the surface area, increase the rate of dissolving. So I thought I would do a demonstration on oxygen in water. So if you look it up online, you'll find stuff like this. But what does that mean? So I turned it into a percent. I turned it into a parts per million. And I turned it into moles per liter, which you now know. Okay. So it's not very concentrated. If you don't believe that, ask a fish. So I also did a calculation where I looked at the concentration of oxygen in air versus the concentration of oxygen in water. The ratio turns out to be about 28:1, which means for oxygen, there's 28 times more oxygen up here than there is up here. So you can see why it's going to diffuse into the water a little bit. So here's the solubility of oxygen in seawater. Notice that at different concentrations, it doesn't matter how high you start with. When you increase the temperature, it kind of drastically sometimes decreases. And here's the solubility of oxygen in fresh water versus seawater. So why would there be less oxygen in seawater? So what is the reason why oxygen dissolves in water at all? Because it crashes through the surface and bounces around until it basically bounces out. And what's the difference between fresh water and seawater? Which one is more dense? Seawater is much more dense. It's more difficult to crash through it. So here's an aquarium. There's a fish. Looks like he's not too happy. Most likely it's because he's not getting enough oxygen. So how would we get oxygen to that fish? First of all, we have to make sure that the temperature of the water did not go up, because that causes oxygen to leave. What else could we do? If you increase the partial pressure of oxygen over here, you would increase the partial pressure of oxygen in the water, then you would increase the concentration of oxygen in the fish. You have to create that gradient to make sure you get oxygen to the fish. You could also increase the total pressure. For example, put your fish in a hyperbaric chamber. Okay. And then finally, what is the air pump doing? Is it pumping oxygen into there? No. All it's doing is pumping air in there. So these are bubbles full of air. All the bubbles are doing is effectively increasing the surface area between the air and the liquid. That's all it's doing. Might stir it up a little bit as well.
Wait, so what does the air bubbles do at the surface that helps?
Every bubble has a large surface area, right, between the air and the water. So which would be better for the fish? If I had a tank like this, where I had a large surface area, or if I had the tank go like this, with only a very small surface area?
Oh, that would be worse, right?
That'd be way worse, wouldn't it?
Yeah, less oxygen.
Yeah. So we call those goldfish bowls because goldfish are able to go swim to the top and gulp air, essentially. Not all fish can do that. Yeah. Anyway, this is one of my favorite cartoons of all. I remember my kids were in high school, they would do that. And I asked them one day, hey, how come all you kids go sag around with your underwear hanging out? Oh, we're all trying to be different. And I said, oh, you mean like you're trying to be different like all those other kids over there? Yeah, that made them think. Oh, I love this one here. Yeah, so they invented a harassmat suit. So that way nobody can harass you and you can't harass anybody, and yeah, society. Okay, so any questions on this chapter? because that really completes Unit 4. So Unit 5, first chapter of Unit 5, essentially is Solutions Part 2. So this will not be on exam 4, this is on exam 5. But I separated these, on purpose. So in biology, we really use about 77 types of concentrations. So moles per liter is one of them. But here's some other ones. The mass percent, the percent mass per mass, or the percent weight per weight, is really the grams of solute dissolved in 100 grams of the solution. So what does it mean if you have a 2% mass per mass solution? That means you got 2 grams of solute in every 100 grams of the solution. But the 100 grams of solution was made by adding 2 grams to 98 grams of water. So notice what we're really doing is we're taking the mass of the solute and the mass of the solution and dividing, and we would get 0.02 grams per gram, right? But then we turned it into parts per 100 by multiplying by 100. So the reason why these are convenient to make is because all you need is a way to weigh it. You need to balance a balance, that's all you need. So I could have this read 0, I put the beaker on there and make it read 0. I add solute till it's 2 grams, and I simply add water until I get 100 grams. Stir it, and there's the solution right there. So the calculations that go with this, I would really highly suggest that you expand the use of units, because it's grams and grams. Why don't we just say grams of solute versus grams of solution? Here's what I mean. What is the percent mass per mass when 5 grams of sodium hydroxide are dissolved in a final volume of 60 grams? Okay, so that's 5 grams of the solute, 60 grams of the solution. You see how I'm making it easy on myself? Divide and then multiply by 100. How many grams of sodium hydroxide and 100 grams of a 12% mass per mass solution? So what did we say about the solution? It's always going to be your conversion factor. I have to understand that this 12% means 12 grams of solute in every 100 grams of the solution. And this is 100 grams of what? The solution. So I cancel out grams of solution, and I end up with grams of the solute. So here I graphed for that solution, grams of the solution versus grams of the solute. I get a straight line passing through the origin. What is the slope of the line? Oh my God, it's our concentration. The next one is volume per volume percent. So that's the milliliters of solute for every milliliters of solution. So this would be an example where you have a liquid solute and of course a liquid solvent. So a 2% volume per volume solution means that there's 2 milliliters of solute in every 100 milliliters of solvent. But that was made by taking 2 milliliters of solute and adding 98 milliliters of solvent to get the 100. So in this case, we do the division, we get milliliters per milliliters, but then to turn it into percent, we multiply by 100. So what do I need to make a 2% volume per volume solution? I need a way to measure the volume. So a graduated cylinder, for example. I would add my 2 milliliters of solute and simply add water until I got the meniscus at the top of the 100 mil mark, and then stir it. Let's just do a problem down here. So how many milliliters of ethanol in 20 liters of a 2% volume per volume solution? So I have to realize that this is my conversion factor. That means that there's 2 milliliters of ethanol in every 100 milliliters of solution. And this 20 liters is 20 liters of what? The solution. So because this is milliliters, I had to change this to milliliters. I'm canceling out milliliters of solution, and there's my answer right there. So proof is about twice the percent volume per volume. So 12% volume per volume, like on a bottle of wine, is about 24 proof. Rum 151 is 151 proof, which is about 75% volume per volume. Okay. So by the way, why is rum so, I don't know, prevalent maybe? It's because solutions of alcohol greater than 70% will burn. So in restaurants, all those desserts that they set on fire and everything, that's all, it's rum 151 for the most part, because it will burn. So then we can combine the two, mass and volume. And this is what's more prevalent really in a laboratory situation. Because in laboratory situations, we have to constantly be worried about volume. You can't do some calculation for a drug and you're going to end up putting, 5 milliliters of the drug into a cell, because a cell doesn't have anywhere near that volume, right? So 2% mass per mass solution means that there's 2 grams of solute in every 100 milliliters of the solution. So notice that we simply do the division, get grams per mil, and then we turn it into parts per 100 by multiplying by 100. It's a little bit more work to make this kind of a solution, but it's much more useful. You need a balance, and you need a way to measure the volume. So if we just do a problem, I'll just grab one of them. How many moles of sodium hydroxide in 66 something milliliters of a 25% mass per volume solution? I have to realize that this is my conversion factor. That means that there's 25 grams in every 100 milliliters of the solution. And this is milliliters of the solution. So I do this and I get grams of the sodium hydroxide. But they wanted moles. So what's the other conversion factor I know? I know how to get from grams to moles. Simply the molar mass. So once we did grams per mil times 100, which is really considered parts per 100, what the heck is parts per million? What does it mean, a 2 part per million solution? For every 2 grams, there's 2 grams in a million milliliters. So again, I'm taking grams per milliliter, just like how I did above, but instead of multiplying by 100 to get parts per 100, I'm multiplying by 1,000,000 to get parts per million. So 2 ppm means that there's 2 grams of solute in every 1,000,000 milliliters. And that's the conversion factor that you would use. And what's related to ppm? ppb, parts per billion. That's the grams of solute in 1,000,000,000 milliliters. And ppt could mean parts per 1,000 if you're an oceanographer, but if you're not, then it means parts per trillion. 1,000,000,000,000 milliliters. So how would you make 20 liters of a 2 parts per billion solution of sodium hydroxide? Okay, well, 20 liters is the same thing as this many milliliters. Get rid of milliliters, keep grams, and I need that many grams to go in 20 liters. You know what? You can't weigh that out in the normal research lab. It's too small. We can weigh out okay in about that decimal place. Some balances in this decimal place, but not very many balances in that. If I'm going to weigh something over here, I don't know if you can even see it, probably not, but we need a balance that has stabilized from vibrations from the air conditioning and people walking in the building. You can't breathe on it, so it's behind, it's all blocked from any wind currents like air conditioning and stuff like that. And once you have all those safeguards in, you might be able to weigh in that place. So I'm just trying to emphasize to you that there's a big difference in ppm and ppb, ppt. So notice the calculations I did here. TCE, trichloroethane, was found in the drinking water up in Mililani town. It came from a dry cleaning company up there. And so they remediated it. They got it out of the water system by bubbling air through the water towers. But anyway, how many grams of TCE in 2 liters of a 4.2 parts per million solution? Notice that, okay, 0.008, I could actually measure that. What if I'm talking about parts per billion? Notice that this is a factor of 1,000 times less. Parts per trillion is another 1,000 times smaller. So these concentrations are used often in chemicals that are found in the environment as pollutants. So if you say in the newspaper, a 1 part per million versus 1 part per trillion, do you think there is much difference between a part per million and a part per trillion? Look at that. It's a factor of 10 to the 6th difference. This is 1,000,000 times less concentrated than parts per million. But the public has no clue. They don't know the difference between a parts per million and a parts per trillion. If they see anything, they simply freak out. Oh my God, we're all going to die. The Republicans did this. They're poisoning our children's future. It's like, chill. You got to look at the data, see what we're talking about. Because in fact, we can measure anything we want to if we really want to measure it. So I'm going to show you a few examples. So you can make columns like this. You can figure out what kind of chemistry you need and make the column material over here to absorb anything that you want. Anything. The chemistry is just incredible. So here's an idea. Say you had an Olympic-sized swimming pool, and I calculated its volume, and it contained 8 parts per trillion of TCE. Okay. So now I want to measure this very, very low concentration of TCE in the swimming pool. How can I do that? Well, I figure out what chemistry I need to have in this column. So I can pour some through here, and every single molecule of TCE binds to that column. You get it? So I could pass the entire swimming pool through that column if I wanted to. It says how much work, how much effort do I want to put into it? It may take you months to pass that whole thing through, that column, but you get every single molecule of TCE to stick on it. Some people say, oh yeah, you purified the water. Yeah, we did. And then I can change the pH, I can change how much salt is in it, I can change whatever to make that TCE come out of the column in a very concentrated form. So what I did, this unmeasurable amount, okay, I collected 0.0024 grams from the entire swimming pool. And say I got it into one test tube that was 1 milliliter. I just did a 0.3 billion fold concentration. You see my point there? We can measure anything. I remember several years ago, I think it was the Sierra Club, they came out with a warning to hikers: don't go hiking in the mountains in Hawaii because there's mercury in the soil. And like, we're all like, mercury in the soil? And I do have a friend who at that time was an expert on heavy metals in the ocean. He was in the oceanography department. And we were talking about it, and he's like, yeah, well, we can measure that in any dirt because mercury just comes out of the volcano. What can you say? The volcano does not follow the EPA rules. So here's another example. This is called Draeger tube technology. And so here's a handheld pump, and this is a tube. So you can go and order Draeger tubes that will simply measure the amount of almost any chemical in the air. So this is just for ammonia. So that could be a problem in an industrial situation, right? So you think you might have an ammonia leak in one of your, say your company's labs. So you open up the door and you stick that handheld pump in there. And if you see it start to change color, there's ammonia in there. You could put a different kind of pump on a robot and have the robot drive in there and sample for you. Say you've heard of sick buildings, right? Where the people in there get sick after long-term exposure. What is the chemicals that is doing that? Well, you could make a bench or floor type model of this, and you could run it all day. Matter of fact, you could rub it all week, or run it all week, or all month, or all year, until you start to see something. Just depends how much you really want to measure that substance. That's what it really depends upon. So we can measure pretty much anything. So questions so far? Molarity we just covered. Okay, so I just put it in here for the sake of completion. This was chapter 17. Then related to molarity is the osmolarity. So what the heck is an osmole? It's a mole of dissolved particles. And here, the identity of the dissolved particle is not important. We count both anions and cations. We count everything that's dissolving and forming a particle in the solution. So 1 mole of sodium chloride, when it dissolves, will give you 1 mole of sodium, 1 mole of chlorine. But that's 2 moles of dissolved particles. So for sodium chloride, 1 mole is equal to 2 osmoles. For sodium phosphate, 1 mole will give you 3 moles of sodium, 1 mole of phosphate. So the conversion factor is, for sodium phosphate, 1 mole is equal to 4 osmoles. Your glucose, when you dissolve it in water, doesn't do anything. So 1 mole is equal to 1 osmole. So let me ask you a question. Is this a direct proportion right here? The conversion between moles and osmoles, is that a direct proportion? Yes, it is. And is it just stoichiometry? Yes, it is. 1 of these gives me 2 of those. 2 of those will give me 4 of those. 0 of these will give me 0 of those. So we can convert back and forth between osmoles and moles, and between osmolarity and molarity. So convert osmolarity into molarity for a 6 osmoles per liter sodium sulfate solution. I have to write this out to get the conversion factor between moles and osmoles. And then you can see I'm just canceling out osmoles and keeping moles. Let's go down to the hardest one. What is the osmolarity of a solution containing 25 grams of sodium sulfate in 2 liters? So I need this conversion factor. 1 mole gives me 3 osmoles. So I got 25 grams, convert that to moles, then into osmoles, and that's in 2 liters, so that's osmoles per liter is half of that. You could also solve it a different way. The good thing about the method that we're doing, you're multiplying by 1. Multiplied by 1, got the answer, then we multiplied by 1. So the order of multiplication is not important. So there's more than one way to calculate most of these problems. And the last one is called normality. This is equivalents per liter. So what the heck is an equivalent? An equivalent is either a mole of positive charge or a mole of negative charge. Okay. So the equivalence is equal to the moles of the ion times the charge of the ion. Okay. So let's just do some stuff. How many equivalents in 0.001 moles of sodium ion? Okay, so 0.01 moles at 1 equivalent per mole is 0.01 equivalents. How many equivalents in 0.001 moles of phosphate? 0.001 moles times 3 equivalents per moles, because of that -3 charge, is 0.003 equivalents. So here's why we use the word equivalent. To make a solution has to be electrically neutral, right? It can't be charged. So if I have a solution with 0.003 equivalents of phosphate, that means I need 0.003 equivalents of sodium to make it a neutral compound. So look at, not even in solution, let's just look at this. 1 mole of sodium phosphate gives me 3 equivalents of positive charge and 3 equivalents of negative charge. So for sodium, here's how it was calculated. We had 3 moles at 1 equivalent positive charge per mole. For phosphate, we had 1 mole, but at 3 equivalents of negative charge per mole. So we see we get these equal. So what is the conversion factor for sodium phosphate? 1 mole is equal to 3 equivalents. We do not add them up. If I got 3 equivalents of sodium, I have to have 3 equivalents of phosphate. So here's another example of that same correlation. We do not add them. So here's a solution with 3 equivalents. Here's a solution with 3 equivalents. Here's a solution of 3 equivalents. So most textbooks, they talk about equivalents in the same chapter as they're talking about acids and bases, because this is really important. I don't do that. I want them all in the same category in the same chapter. So how many equivalents of magnesium ion in 6 moles of magnesium phosphate? Well, here's how I got my conversion factor between moles and equivalents. So I get 6 moles of magnesium phosphate, 6 equivalents of magnesium for every 1 mole. That gives me 36 equivalents. Convert moles per liter into equivalents per liter. Okay, so I have to know that these are conversion factors, both of them, right? I have to know what they mean. So I got 6 moles per liter, and I got to get rid of moles and keep equivalents. So that's 36 equivalents per liter, or 36 N. Then I started using milliequivalents, because this is often what we use in clinical situations like IV bags and things like that. It may or may not be in equivalents or milliequivalents, but oftentimes they are. So how many milliequivalents of phosphate in 6 milliliters of a 2 moles per liter solution of magnesium phosphate? Well, I know I need this conversion factor. So I got 6 milliliters. Here's the moles. So then I turn moles into equivalents. Then what else did they want? Oh, milliequivalents. There's 1,000 milliequivalents is equal to 1 equivalent. It's like 1,000 milliliters in a liter, right? And yes, you can do these different ways. So anyway, to summarize, here's our 7 types of concentrations. These are the ones that are based upon solute mass or volume, right? Mass per mass, volume per volume, mass per volume. And what's related to mass per volume, of course, is ppm, ppb, ppt. And then here's the ones that are based upon moles in some way. So moles per liter, osmoles per liter, equivalents per liter. These you add up, equivalents you don't add up. So regardless of how complicated it might look, it's all simply conversion factors. And the concentration is always going to be your conversion factor. So any questions so far? So that's the math that people hate, but I always try to temper it with more important things. For example, colligative properties. So a colligative property is a property of the solvent. It's a property of the solvent that changes depending upon the concentration of dissolved particles. It does not depend upon the identity of those particles. There's no chemical reactions going on. This is just physical properties of the solvent that change when you add solute to it. So doesn't that seem like we're talking about osmoles right here? In fact, yes. But as you see, the relationship between moles and osmoles is a conversion factor. They're directly proportional. Every single concentration is directly proportional to the other concentrations. But it is more closely correlated to osmoles per liter. So the first one we'll look at is osmotic pressure. And this increases with increasing concentrations of solute. So what do we need to look at osmotic pressure? Well, we need two different concentrations, and we need what's called a semi-permeable membrane that lets certain things through and other things can't go through. And if you think this is some foreign, unrelated concept here, every single cell membrane in your body is a semi-permeable membrane. Like say your capillary veins, for example. What is that made out of? Cells that are all bumped up against each other, and they're sealed where they interact right there. So the only way for you to absorb something from your blood into the tissue is to go through a cell membrane. Some things are allowed, some things are not allowed. So two important processes. Osmosis is the movement of the solvent through the membrane, where dialysis is the movement of solute through a membrane. So right now, we're talking about movement of the solvent through the membrane. So here's the basic scenario. I have these two sides of this U-tube that are equal. That means that the pressure here is equal to the pressure here, right? There's a semi-permeable membrane right there. And say I don't have any particles in here yet. So if I were to push down on one side, I would see the solvent pass through. Then when I let go, then it would pass back, and these would go right back to the same height again, right? So what happens when I put this solute in here that is not able to pass through the semi-permeable membrane? Well, diffusion wants to happen, right? Diffusion always goes from the more concentrated to the less concentrated. But here's the problem. The solute cannot pass through the membrane. But we're not talking about solute in this case, we're talking about solvent. Now, where is the solvent the most concentrated? When I put this solute in here, I displaced solvent molecules. So I'm telling you that the concentration of solvent is higher over here than it is over here. So we oftentimes concentrate too much on diffusion of the solute particles, but now we're concentrating on the diffusion of the solvent. It will go down its concentration gradient, move in this direction through the membrane, that's called osmosis. And when that happens, you'll see that this will be higher than over here because of diffusion of the solvent. And osmotic pressure is considered the pressure I would have to push down right here to make these two levels equal again. That's what osmotic pressure is. So to determine the direction of osmosis, you find the side where the solvent is the most concentrated. So that's really all we have to do with this. We don't have to do any calculations, but I'll just show you something. Osmotic pressure is usually given that symbol, capital pi actually. And look at the ideal gas law. So I simply solve for pressure, right? And then I took N and volume and put them underneath each other. R is a constant. And at a certain temperature, if you take the temperature constant, that's also a constant. And all I did is rename this as osmoles per liter. Now it's called the osmotic pressure. That pressure becomes the osmotic pressure. And why can't we use the same ideal gas law? Because whether it's in a gas or whether it's a liquid, the particles are bouncing around any direction they happen to go because of the laws of motion, and they simply diffuse. And we assume that there's either no attractions or the attractions that are there are not important under those circumstances. So the mathematical description is the same. And then in this red box right here, all I was trying to do here, you know, I have to prove things to myself before I start trying to tell you folks about it. I can't be talking about stuff I don't know about. Unlike a lot of people that you may know. So I proved it to myself by doing this proof right here that when you add solute to water, you are displacing water molecules. So I had to prove that to myself. So here's the proof of that. So here's some practical examples of osmotic pressure. Here's one of the tallest trees in the world. It's 38 stories high. And how does this tree get water from the ground to up here? How does it do that? Well, it uses osmotic pressure. Well, what is osmotic pressure? How does that work? Why does water go into the root of any plant? Is osmosis. So the plant has to have osmotic particles in the root cells to osmose the water into those cells. Then it has to have it all the way up here as well. So the water travels up the xylem and the phloem, and then botanists will talk about transformation, which is simply evaporation off the leaves. It sucks more water in there, but nevertheless, how does a tree get water all the way up here to its leaves? It has to do the same work as if you were to take a bucket of water and climb with it up that tree. It has to do that same work. Moving water up there is work. And it uses osmotic particles to do that. So, take a sugarcane plant, for example. Why does the sugarcane plant have sugar in it? Is it because it wants to enrich the life of humans and make us overweight and everything? No. The only reason why sugarcane has sugar in it is because that is the particles it uses to cause osmosis to get water into the root system. So here's a typical plant cell. So in here somewhere you'll see the cell membrane, and then what is all this stuff here? That's the cell wall. So these cell walls have to be extremely strong. Matter of fact, they're so strong that we use wood to build houses and stuff. So let me just ask you a question. Say this was a hollow tube of somehow, maybe plastic pipe or a metal pipe, and we started pouring water to fill it up. You know what I'd be afraid of? There'd be so much pressure right here from the gravity pulling down that column of water that that pipe would simply explode. That's how much pressure there is down here. It's tremendous. And in fact, every time I walk by a tree, I'm like, oh, please don't explode right now. And oftentimes you see trees hit by lightning and they do explode because you're heating up the water, making some of it go into vapor phase, right? Causing an increase in the pressure. Anyway, another human thing that I have a problem with. Let's find a really, really combustible material, wood, that loves to burn, and we know it because we've been burning it for 1,000,000 years, and we'll build a house and live in it. Anyway, interesting concept. But what about animal cells? We don't have cell walls. So we have a problem with that. We can't counteract pressure. So here's what happens to cells. If we put them in what's called a hypotonic solution, wait, I got these reversed. Here's a hypertonic solution. Here's this one over here, the one that I drew. What does that mean? I have more solute outside the cell than I do inside the cell. So where is water the most concentrated? Inside the cell. Which way will osmosis of water occur? It will go outside the cell. Red blood cells start to shrivel up like this, and we say that they're crenated. So if I take a blood sample and I look at a dehydrated person, what is the blood sample going to look like? It's going to look like this, crenated. If I take a hypotonic solution, there's less particles outside than there is inside. Where is water the most concentrated? Outside, so osmosis is going to go in that direction. What will happen to those cells? Well, here's a hypertonic solution. More water goes in than comes out. Wait, I'm sorry, over here. And look, some of them are breaking. Clinically, that's called hemolysis. You find heme outside the red blood cells because the red blood cells have broken. People die from either situation, which is why the state of hydration is so important for you to stay alive, and the state of your electrolyte solutions in your blood is so important. In emergency medicine, they come up and find somebody on the street, they don't know what's wrong with them. What's about the first thing they do? Is put them on IV. Normal saline IV. because they may not know if the water is correct in the blood or if the electrolytes are correct in the blood, but this is going to correct both of them at least to some extent. That's how important it is. What we want is an isotonic solution. So the rate of water in is equal to the rate of water out. That's what I have over here. See that? The solutions are isotonic. It may be different ions over here than over here, but they're at least equivalent in terms of osmoles per liter. So here's some IV solutions that are in common use. So the osmotic reference value is about this. That's where I got the 0.3 from that I put in that picture up there. Here's normal saline. It's about 0.9% sodium chloride in water, which is about 0.3 osmoles per liter. And then we have D5W, which is 5% dextrose in water. Dextrose is glucose, or your blood sugar, also about 0.28 maybe. Then we have D5 normal saline, which is 5% dextrose in normal saline. So that is a very high osmotic pressure right there. So because of that, they often use instead D5 half normal saline. So it's a little bit closer. Okay. And oftentimes they will use Ringer's solution. Oftentimes it's lactated. So here's the milliequivalents of different things that are in there, including lactic acid. Let's see. So it's about 0.28, which is similar to D5W. And lactate does two things. It helps stabilize the pH, and also provides the lactic acid to be used to make, so the patient can make their own blood glucose. That process is called gluconeogenesis, where lactate is converted into blood glucose. Anyway, that's just for your edification there. What is dialysis then? Dialysis is not a colligative property, but it is related. Dialysis is movement of solutes through a membrane. So you know about kidney dialysis, right? When your kidneys are no longer good at removing waste products from your blood. So here's blood with waste products like ammonia, urea, a bunch of other stuff, right? It comes through the machine, and if the waste products are higher in concentration here than they are in the machine, they're going to dialyze out of the machine, down their concentration gradient. But everything, pretty much everything, can pass through this artificial membrane right here. So what if you put together the dialysis machine and you forgot to put glucose in the machine? What's going to happen to your patient? Well, they'll go hypoglycemic, won't they? They could die from you removing all the glucose from their blood. So that means all the good stuff has to be here in equilibrium. That means that you have to change this solution a lot, and that's expensive. Kidney dialysis is extremely expensive because all the stuff has to be sterile, it has to be biologically correct. It's an invasive technique, so you have to have qualified health professionals there. It's expensive. Better, you should just take care of your kidneys, right? So dialysis and osmosis can go in the same direction or they can go in opposite directions. Anyway, so another one that takes less time is the equilibrium vapor pressure decreases with increasing amounts of solute. Why? Again, here's how we measure the vapor pressure, right? So if I start adding solute in here, what happens? Well, if that solute dissolves in the solvent, there must be attractions between themselves, right? So to get the solvent to evaporate, to increase the pressure up here, then you have to break those attractive forces. Usually those are going to be stronger. And the other factor is that the more I block access to the surface by putting something there, whether it's an oil covering or a bunch of solute particles, I'm blocking access to the surface where evaporation is taking place. Okay. So, which one evaporates more quickly, fresh water or salt water? Fresh water, right? Takes a very, very long time for seawater to evaporate. The boiling point increases. Say you're boiling water and you're going to make Cayman. You open up the pack, you pour the Cayman in, the salts in. What happens? It stops boiling. And a couple of minutes later, it might reboil, but when it boils again, it's boiling at a higher temperature. That's what we mean. Why? It's for the same two reasons. In this case, if you're boiling water, what's in that bubble is water. So we don't care about this surface, we're talking about this surface now. And that's the same thing. You have to break attractive forces between the solute and the solvent, and the solute is physically blocking access to the surface of that bubble. And then the freezing point decreases. So which freezes more easily, fresh water or salt water?
Fresh.
Yeah, you've seen pictures of icebergs floating around in the ocean, right? The icebergs are still frozen, whereas the sea is not frozen. So the freezing point decreases. It has to be colder to freeze salt water than to freeze regular water.
Is that also because the ocean is constantly moving?
Probably not as much, but kinetic energy is related to temperature, right? So, yeah. But it turns out it's for the same two reasons. So instead, you're going from the liquid and you're trying to join up with this growing crystal. So you're talking about this surface right there. But it's the same two principles. The solute and the solvent are attracted to each other, so you have to break those attractions. Then the solute physically blocks access to that growing surface, that growing crystal. So freezing can actually be used to purify water. You ever pull out your ice cubes and look at the bottom and you see all that kind of white stuff at the bottom of the ice cube? And then if you let the ice cube just melt, you see all this white stuff kind of sitting there on the bottom. Those are all the salts and stuff that was dissolved in the water. So when you start lowering the temperature, the solubility of those salts decreases, so they start to precipitate. Then as you're forming water crystals, it's excluding the solute particles. Anyway, so here's a practical example. When I was a kid, we had the crappiest cars you would ever believe. To go surfing on the North Shore, you'd have to take all kinds of water with you because your radiator would boil over and everything. And I thought, God, only rich people are going to put radiator fluid in there. That costs money. But here's the reason why you would put radiator fluid in your radiator. It's because of the colligative properties. The vapor pressure is lowered, the boiling point is raised, and the freezing point is lowered. Okay? That's why it's called antifreeze. And in addition, you have anti-corrosion additives that protects your freeze plugs, protects your water pump, all kind of stuff like that. So, yeah, so volatile solutes like ethanol and stuff, will affect equilibrium vapor pressure, of course. Anyway, there are some differences. And here I was just talking about all methods of preserving food use the same strategy. Make water less available for microbial growth. Freezing, dehydrating, salting. What does salting do? Uses osmosis. You suck the water out of those microbes and they can't grow. They can't grow, they can't metabolize, they can't make toxins. So I put this in here just to be a little bit more comprehensive about clinical uses of all this stuff. So you look at certain electrolytes, they're either going to be millimoles or milliequivalents, something like that. They have units, they like to use the deciliter because that was like during the time of these inventions was a convenient measure, right? But here's something really interesting. The comprehensive metabolic panel, the tests are done with an autoanalyzer. That was first invented in 1957. Is that crazy or what? So anyway, so that kind of completes that chapter.
I like that one with the ice cream.
Say again?
I like that meme with the ice cream.
Yeah, I know.
It's pretty cute.
Yeah. My friends I surf with, they all have dogs and everything, and they love their dogs. Somehow the wives don't get overjealous. But man, recently I've been watching them, they let their dogs lick their face. I'm like, oh my God, where's that dog's tongue been?
I know, right? I didn't know. I feel like everyone I don't know how people choose to ignore that. Like, it's kind of gross.
It is actually.
Did you hear about the guy who let his dog lick his leg wounds, and then he had to become amputated?
Oh,
because of him.
really?
Yeah,
Okay.
pretty bad.
Dang, that's terrible.
Yeah.
Why would you let somebody lick your wound?
Oh God.
Love your dogs, right?
Gosh, people, man.
And the dogs, like we come out of the water at our friend's house and the dog comes up to us and starts licking us. And we're like, oh yeah, the dog loves us. And I'm like, no, it just wants the salt.
So funny.
But my wife is Muslim and she's from South America in a third world country. And they don't have pets over there. Although she did say her grandmother had a pet monkey. So dogs are mean, so they don't have pet dogs, right? Dogs are watchdogs.
Hmm.
And so for many years, she was like, what? You were hanging out with dogs? Don't touch me, go wash your clothes, whatever, So finally, I found this imam who has researched the whole Quran and everything else. And yeah, there's nothing in the Quran that says that dogs are dirty or immoral or anything like that. So that saved me. But on the other hand, you have to be aware of cleanliness.
Definitely.
But when all those religious books were written, the germ theory was unknown.
Mm.
So anyway. So if you haven't taken exam 2 or 3 yet, whichever course you're in, you need to do that today, right by 9 p.m. This is the first chapter in the last unit.
How many more chapters are there?
It goes through 21.
21.
Yeah.
Okay.
Yeah. So anybody have any other questions about anything?
I have a last minute question on the periodic table.
Yeah.
When you're looking at a reaction and you're trying to figure out which direction it goes in, how do you determine which is the more reactive element? So on the homework, how would you know that, say, gold is more stable than aluminum?
Okay, so that's in the chapter on chemical reactions. So there is a whole section on there.
Okay.
And that's where the
That makes
activity
sense.
series comes in for
Oh,
simplicity
that's what it is.
reactions. Yeah.
Okay,
So,
that's right.
but you're only going to be asked about your common knowledge. I mean, gold is simply stable as heck, right?
Mm-hmm.
And your aluminum oxidizes. So, yeah. So we're just going on that essentially.
Okay, sounds
The
good.
periodic table is hard to discern. It's hard to make judgments unless you really, really know a lot, which we don't, right?
Mm.
We're just humans.
And then hexahedral is the same thing as bipyramidal.
Yes, right. 2 different
Okay.
ways. So one
Oh, okay.
describes how many sides there are, right?
Uh-huh.
And the other is more like talking about the skeletal-like structure of it.
Okay, got it.
Yeah.
Thank you.
Okay, so anything else? Okay, well, you guys have a great day. This will be posted up on YouTube as soon as I can get it there.
Thank you, Professor.
If you have any more questions, just email or post in discussions. Yeah?
Thank you.
Okay, you guys have a great day. See ya.